Hello dear students, I hope you are having a great time in learning this course of artificial intelligence. Let us continue our discussion on what we have learned yesterday. So today what we will study is, or what we will discuss is regarding uninformed search strategies. Uninformed search strategies in the other way are also called as blind search. There is no extra information other than what is given in the problem. Based on that information only, the problem need to be solved. So uninformed search strategies use only the information available in the problem definition. Now, what are the different uninformed search strategies we can have? In case of artificial intelligence, we will go through these. There are around 5 artificial intelligence related, uninformed search strategies. The first one is breadth first search. The second one is like uniform cause search. The third one is depth first search. The fourth one is depth limited search. The fifth one is iterative deepening search. I am very sure you might have already come across of breadth first search and depth first search in case of your data structures course. We will see these things once again here in a different perspective. So, what is this breadth first search? The basic idea of breadth first search, as we call it as one of the strategy. Now, based on the going back to this discussion of our fringy, the order of placement of successor nodes into the fringy and how you pick out the element that defines the strategy you are applying, right? That is what we have discussed earlier. So what happens here in case of breadth first search is the implementation is based on fringy is a FIFO queue. Fringy is a queue which now will follow first in first out order. That means the new elements which are being joined will be joined at the end. The first element which is inserted will be removed first. So it is like FIFO, first in first out. So expand in, when we expand that in such a way, what we will get is we will be expanding the shallowest node first. So breadth first search follows the principle of expanding shallowest unexpanded node first, and it implements based on fringy, which is a FIFO queue. That is, new successor goes to the end. For example, let us consider this, such a tree. We are starting from A, and let us assume we need to go to the goal G. How it will go? Like first A is inserted into the fringy and it is picked up, and A generates successors of B and C. B and C gets joined into the fringy at the end. So B will be the next one to execute or pick up and continue with the search. Let us see this. So after A, we are coming for B, and after B, we will not go to D, but we will not go to D, but we will go to C in the shallowest way, because C is already in the fringy and first in first out. When we explore B, the successor function will give me two nodes D and E. These D and E will be pushed to the fringy at the end after C. So after B, anyhow we got D and E, but we are not exploring D and E. First we are going to C. Then from C we will come to D. C generates F and G, which will be pushed onto the FIFO queue. But that will not be the one which we will be visiting next. We will be, because already D and E are there. So D has come first, first in first out. D will be the next one to visit. So in such way we will be going on visiting all the nodes. As we can understand, any such strategy or any such algorithm stops when we reach the goal state. If we consider G as a goal state in the previous example, then it will stop at G. Now, the properties of breadth first search. for any search algorithm, we have discussed that we will evaluate the search algorithm based on 4 properties. First one is complete, second one is time, third one is space complexity, and the fourth one whether it is optimal or not. What is complete? If the goal exists, if the goal state exists, whether the algorithm is able to find the goal state or not. That means, is it evaluating all the options available, all the state space available, or is it leaving any states? So whether it is complete or not. In case of breadth first search, it is evaluating all the nodes which are available. So yes, it is complete. It is complete. When it is complete, it depends on the number of children the node is having. So if B is finite, then it is complete. If B is infinite, that means the expansion is happening and happening and happening. So the search will never end, right? Now, time complexity. When it comes for the time complexity, as what we have already discussed, time complexity is based on the number of nodes that are getting generated. How many nodes will be getting generated in case of a tree with B branching factor? For every level, we will get multiples of B. So it goes like 1, which is the root node, first one, 1 plus B square plus B cube, and so on up to B to the power of D minus 1 multiplied by B. So which can be summarized as big O of B to the power of D plus 1. So that becomes big O of B to the power of D plus 1 would become your time complexity. Then what about space complexity? In this case, space complexity will be same because we need to maintain whatever the nodes that get generated, that will be pushed onto your fringy. So big O of B to the power of D plus 1. Now, is it optimal? Do I get a lowest cost path? The path cost should be smallest. So that is what optimality is based on. Yes, if we consider cost is equal to 1, equal cost we are going with, then it would be the optimal one. The problem with your breadth first search would be high space requirement. Space is the bigger problem more than the time in case of breadth first search. That is the major disadvantage. Now we will discuss the other strategy. In the previous case, we have considered the strategy of FIFO-Q. If it is not FIFO-Q, if I want to implement it in the form of LIFO, last in first out queue, then this becomes another strategy. So before we go for the strategy of depth first search, let me stress on more points regarding with BFS. Consider a hypothetical state space where every state has B successors. So this is the explanation of what formulas we have seen. The root of the search tree generates B nodes at the first level, each of which generates B more nodes for the total of B square at the second level. Each of these generates B more nodes yielding B cube nodes at the third level, and so on. So if your problem has a solution at depth 12, now you imagine at depth 12, that means B square, B cube, and so on, you are getting up to B12. Now given our assumption, it will take 35 years for breadth first search, or in case of uninformed search, to find the solution. The solution is at depth 12. This is the problem with breadth first search. Breadth first search is optimal when all step costs are equal, because it always expands the shallowest unexpanded node. And the other way we can do it is uniform cost search, which expands the node n with the lowest path cost. Note that if all step costs are equal in case of uniform cost search, then that is identical to your breadth first search. So this is something discussion related to the breadth first search. Now we will discuss the another strategy. And this is an example of breadth first search for the 8 puzzle, for your example understanding how the tree structure can be. So here comes the depth first search, which has got an implementation of LIFO fringe. So now the successors are put at front in the fringy queue. So from A, I will visit to B. I have B and C, but B and C are placed in the fringy. I will visit B. B generates D and E. Now in case of FIFO queue, we added D and E at the end of C, but now D and E will be in front of C. So the next node to explore or expand would be D, not C. So that means I am coming in deep, depth wise. So like this, it goes like this. Now from B we have come to D, then we will come to H, and so on, like this. So somewhere our goal, we can consider one of those things as your goal. Now the properties of depth first search will include whether it is complete. No, it is not complete. There is a problem that in case of depth first search, it can fail into infinite depth. Like imagine after D there is another level, there is another level, there is another level, and it's going on. Just imagine like the depth first search for a tree, in case the goal what we need to reach is C. After A we have come to B, then we have come to D. Just C was our goal state. Imagine like this, what is happening, whether it is giving you the better solution or whether it is a safe one. Imagine. So we can modify it to avoid repeated states along the path also. It can be complete only in case of finite spaces. Now the time complexity for breadth first search would come for O of B to the power of M. Terrible if M is much larger than D. But if solutions are dense, that means nearest, not much deep, maybe much faster than the breadth first search. In case of space complexity, it would be O of BM, which is linear space, depending on the maximum of depth M. So here it is doing better. Optimal, obviously it is no, as per our discussion we have already done. So in the worst case, depth first search will generate all of the O of B to the power of M nodes in the search tree, where M is the maximum depth of any node. Note that M can be much larger than D, the depth of shallowest solution, and it is infinite if the tree is unbounded. So we can have a variant of depth first search called backtracking search, uses still less memory. In backtracking, only one successor is generated at a time rather than all successors. Each partially expanded node remembers which successor to generate next. In this way, only O of M memory is needed rather than O of BM. So this is one way of implementing it. The drawback of depth first search is that it can make a wrong choice and get stuck again down, going down a very long or even infinite path, when a different choice would lead to a solution near the root of the search tree. As what I said, B instead of C it has taken. So this is example of depth first search of the 8 puzzle with a depth bound of 5. So happy learning. We will see the next things in next session.